Hey guys, welcome to Ordering Relations with me. Basically all we're doing today is we're going to find the largest and smallest elements in sets. Yes, that does need to be done formally because we're mathematicians. This is like getting dangerously close to real analysis, so I'm like really excited for today. Not quite going to get to some of the things that I'm just like, oh, but I'm excited. I love analysis. It was my favorite. So getting started, remember last time we did like symmetric and transitive and reflexive relations. We're going to introduce a new type of relation called antisymmetric. And remember, symmetric was if xy is in there, then yx is also in there. And the additional thing that we're going to have for antisymmetric is if they're both in there, that means that x is going to be equal to y. So you only get that switcheroo thing when they're equal. So let's consider example 1. We have the relation where x is related to y by having x is less than or equal to y. We want to prove that this is antisymmetric. So we're going to say let xy be an element in R. And then we're also going to have yx as an element in R. And if it's antisymmetric, that's going to mean that they're going to have to end up equaling each other. So we use the definition of R, which is x is going to be less than or equal to y, and y is going to be less than or equal to x. So if we have x is less than y and y is less than x, the only thing that we can do in between is this middle ground, because it can't be bigger and smaller at the same time, but they can be the same. So then x is going to be equal to y. There we go. This is antisymmetric. And the reason we care about antisymmetric stuff is now we get to have a new overarching cool relation. And that's going to be called a partial order. So we have a partial order, R, if it is reflexive, not symmetric, but antisymmetric, and transitive. A set that has a partial order is called a partially ordered set, or poset for short. Very clever. So let's show that R is a partial order. So we have to have that R is reflexive, which, let's see, reflexive and transitive, actually. You guys already did that for me on the worksheet. So thanks for doing that for me, guys. And then we also have R is antisymmetric. That was example 1. So we're already done. R is a partial order. Are there other partial orders? Yes, of course there are other partial orders. This is going to be like the biggest and most important partial order that you'll ever have the pleasure of dealing with, because we like less than and equal to. So with partial orders, what we get to now do is like we have an order for our elements, which means we can talk about things that are going to be bigger than and things that are going to be smaller than. So we're going to say that R is a partial order for the set A, and B is a subset of A. We have alpha is an upper bound for B. So just to draw this out, imagine you have like a line, and then we'll say this line is A, and then B is somewhere in here. We say that alpha could be like right there. So alpha would be an upper bound for B if we have B is related to alpha, like that. I feel like that's really hard to visualize, which is why I introduced the less than or equal to right off the bat. So if we were to use the less than or equal to relation, we would have that. So we've got alpha is an upper bound if b is less than alpha for all the b's in our B. So always keep the less than equal to it sitting in the back of your mind. I feel like it just clarifies everything. But don't write it, because if that's not your partial order, then now you're writing wrong stuff. Okay, similarly, lower bound is going to be beta. So beta would be like something over here. And it's going to be less than everything that's in B. Or, since we're not allowed to assume that our partial order is less than, we would put it like that. So B or beta is related to B. Let's take this for a spin using the best partial order that's out there, the less than equal to. We want to find upper bounds and lower bounds for this first set, 0 to 1, and it's just sitting inside A, which is all the real numbers. So upper bound, all we have to do is find things that are bigger. So like 10, a million, and even 1 works because I said less than or equal to, and all of the other elements in this interval are less than or equal to 1. So 1 is in B, but it is also an upper bound for B. Totally okay. Lower bound, that's going to be something like, again, 0 is less than all the elements in that interval, 0 to 1. It is in B, but that is okay. Negative pi, negative 23, and negative 10,000. I'm pretty sure I said a million when I wrote that 10,000, but I got too lazy to write all those zeros. Okay, so that's for example A. Let's look at the next example. Now we have an interval negative 1 to 1. We're once again going to look for the upper bound and lower bound. I'm just going to duplicate it. So the upper bound actually stays the same. So 1 is no longer in the set. It's been excluded from our set B, but that's totally okay. It is still bigger than anything in B. So 1 is still an upper bound. Same goes for 10 and 10,000. Lower bound, that 0 doesn't work anymore. 0 is now in B, and there's lots of things that are less than 0 in B. So he has to go. But negative 1 would work. And same with negative pi, negative 23, negative 10,000, all of those also still work. Now we're going to do upper bound and lower bound for B, where it is negative infinity to 0. So upper bound, I'm going to steal all of our upper bounds from before, actually. Those are all upper bounds because they're all bigger than negative numbers. And so does 0. I'm going to throw him in there. And then lower bounds, there's nothing less than negative infinity, so lower bound actually does not exist. So that's really important to notice. You're not guaranteed the existence of upper bounds and lower bounds. Okay. Next topic. So remember, these guys were just kind of like special. They were like the borderline ones. And they actually have special names. So that's the least upper bound or supremum. Having the words least and upper right next to each other suck. But that's okay. Let's try and interpret this. So to be a least upper bound, number 1, you have to be an upper bound. Number 2, you have to have that it is smaller than all the other upper bounds, by which I mean it is related using that relation R, which we do not know. It is less than. Okay. So that kind of makes some sense for the words least upper bound. It is an upper bound and it is the least of all the upper bounds. Let's take a moment. We'll come back for greatest lower bound in a second. Let's go back here. We have same relation, same B's. I want to find the supremum and the infimum. So sup B is going to be the largest or the smallest upper bound we can find, and that was 1. So everything below 1 is going to be in B. Everything above 1 is going to be not in B. And then 1 just so happens to be in B. Now we have greatest lower bound. So qualification number 1, beta has to be a lower bound. And then qualification number 2, beta has to be bigger than all the other lower bounds. aka it's related using some arbitrary R that, again, we are not allowed to assume is the less than equal, but it definitely helps visualize what's happening. Okay. Back to the example. The infimum of this B then right here is going to be 0. He is smaller than everything in B, but everything smaller than 0 is going to be a lower bound. And so it is going to be the greatest of all the lower bounds. Let's do it again for a couple of more. So supremum of this B is still 1. The infimum of this B is -1. The supremum of B here is going to be 0. And then remember that this set did not have any lower bounds. And since the very first qualification to be the greatest lower bound is to be a lower bound, it is not surprising that the infimum also does not exist. Okay, I love this stuff. I thought this stuff was great in analysis. And so the book doesn't go into anything like super deep or exciting, but I went and I found an example from analysis that I could prove for you guys. If we've got that B is a subset of A, oh, where's my highlighter? And they're non-empty. We want to have elements to work with, otherwise it's boring. And R is the partial order on A. We want to prove that if they both have supremums, so none of that funky business with like negative infinity or something, then we have the supremum of A, or the supremum of B is related to the supremum of A. aka in the back of our minds, we're like, okay, so the supremum of B is going to be less than the supremum of A. I can kind of see that. If B is contained in A, of course, whatever's supremum of A is going to be bigger than B. I can see that. Okay, but I did not say that was the partial order that we were using on these sets, so we're not going to actually have it on our page. Let's get started. What are things that we are allowed to assume? We're going to assume that B is a subset of A. We are going to assume that they have supremums, and so I'm going to give them names. Alpha equals the supremum of A, and beta equals the supremum of B. So then what do we have? Well, we have the definitions of supremum. And that said, we have to have upper bounds and the smallest upper bound. So what I'm going to do, where this argument is headed, is I want that guy to be an upper bound for this guy, or for, I want that upper bound to be an upper bound for B. Because if it's an upper bound for B, I know things about the upper bounds of B. I know that they're bigger than or equal to this beta. Okay, gonna write that out now. So we've got alpha is the supremum of A, which means that alpha is an upper bound for A. That is the definition not of upper bound, that is the definition of supremum. So then if alpha is an upper bound for A, alpha is an upper bound for B because B is part of A, since B is a subset of A. Right, because alpha is going to be bigger than all the elements of A, which means it's bigger than all the elements of B, since all the elements of B are elements of A. Okay, then now we're trying to get back to how beta is related to alpha. So beta is the supremum of B. So let's go back to here. Let's talk about beta. Beta, since beta is the supremum of B, we know that beta is going to be less than gamma. Oh, did I say less than? I mean beta is related to gamma for all the other upper bounds. So for all gamma, for all upper bound gamma of B. So beta is less than all the other upper bounds of B. But alpha is one of the upper bounds. I just showed that it's an upper bound. So now we can say, and then beta is less than alpha. Oops, I mean beta is related to alpha because alpha is an upper bound of B. So there we go. That's what I just wanted to prove. Beep, beep, beep. So that's kind of like a cool thing from analysis that we can bring here into 381. And you probably enjoyed that much less than I did, but I had a blast. I'll see you all next time.